Right, good afternoon, everybody. My name is Mohammed Rezal. In short, you just call me Rezal. So I'm from Malaysia. It took 14 hours to get here. So this is V1.3 with reference to Professor Bernstein's comments in the forum, if you're following it. And, well, let's just go through it. Right. The idea behind this design is not to follow existing methods of designing a crypto system. At least that's what we believe. So it's supposed to be based upon a problem that could be proven analytically to require exponential time to be solved, to be able to be proved analytically that the crypto system is indeed resistant towards quantum computers, to utilize problems mentioned in point 1 above in its full spectrum without having to induce weaknesses in order for a trapdoor to be constructed, to use simple mathematics in order to achieve maximum simplicity in design, such that even practitioners with limited mathematical background will be able to understand the arithmetic, to try to achieve 128 and 256 bit security according to the ECC length, to achieve maximum speed among having simplicity in design and short key length, to have a sufficiently large signature space, the computation overhead for both signing and verification increases slightly, even if the key size increases in the future, to be able to be mounted on hardware with ease, and the plain text to signature expansion ratio is kept to a minimum. Okay, so the idea is something put into a formal statement, but this is something which is everybody knows actually. If you have a number, let's say you have a composite number, and the length is given by small n, and pk is one of the factors of n. You choose a big alpha inside this interval, and then you do the modular reduction. The question is, if you are given the value capital A, n, and pk, what was alpha? So alpha has already been modular reducted, and the task is to find what is alpha. The complexity is given as follows. If npk is the length of pk, the complexity to obtain alpha is actually O to n minus npk. In other words, if pk is n delta for some delta between 0 and 1, the complexity to obtain alpha is O(n)(1 minus delta. And if you deploy Grover's algorithm, it divides by 2. Okay, then we couple it with Herman May's comments or remarks in 2008. It's about the ability to retrieve variables from a given modular multivariate linear equation. And it comes together with this theorem, which is a well-known theorem. And the remark is as follows. If you have this summation, and if you want to find the solution 0 modulo n, you can have it if the product of the upper bounds is less than the n. But if the product is much larger than the modulus, then usually you have n to the power epsilon many solutions, which is exponential. So from conjecture 1, there's hardly a chance to find efficient algorithms that in general improve from this bound. So we couple this with the modular reduction problem, and we have the following system parameters. Given a parameter, security parameter k, we determine a parameter j, which j is referring to a set of public primes beginning from 3, 5, 7, and so on. And we multiply all of it, give it the variable n. Example, if you use J43, n is 256 bits. Then you choose a random number in Zn of order Gg, where Gg is approximate n delta for chosen value delta, and delta we wish it to be as close as 0. That is Gg, g to the power Gg is 1 modulo n. Then we choose a random prime r inside this group, Z phi n of order Gr, where Gr is approximate phi n epsilon, where epsilon we wish it to be going close to 1. That is, choose R with a large order in Z phi n. Now we let ngr be the length of gr. Such R has its own natural order in Z phi gg. Let that order be denoted as grg. We can observe that the natural relation given by rgr g is 1 modulo gg, and so on and so forth. Then we will choose a random prime, where q minus 1 divided by 2 is also a prime. So then we have our system parameters as follows. G, K, Q, N, R, GG, GRG, N, and N phi GG. So this is the key generation. We choose a random alpha. Then we compute the first public key, which is alpha mod GRGQ. Then we compute our second verification key, which is the hash of this value, alpha to the power 4 modulo q square. Then we publish these two numbers, and this is the private key. As for signing, we will output two signatures. So first you hash the message, then you choose a random R, compute S1, you compute GS1, which is the GCD, you compute GS12, which is the GCD of the following. Now, this parameter 100 is just for illustrating purposes. We choose 100, but we are still trying to find which is the best upper bound. If it's less, then we repeat from step 2. Then we compute S2 as follows. If S2 does not exist, then we repeat, finding a new small r, and finally we output the signature. So the verification procedure is a collection of comments from friends, from Professor Bernstein online on the forum and so on until last week. So first, to verify, we hash a message, right? We retrieve back the GCD value. Then we compute alpha f, which is V1 modulo GRG, and we compute W0 and so on. If W0 minus S2 is 0, then we reject the signature because it is a forged signature. Else you continue to step 10, right? We compute the second parameter W2 as follows. Then we compute W3. If it's 0, then we reject the signature because it is a forged signature. Step 16, we compute W4, then we compute W5, then we compute W6. If W6 is not 0, then reject the signature. Else we continue the process, compute W7 and the following. If W9 is not 0, then you reject the signature. And finally, we compute number 30, which is Z0 RS1 S2, compute Y1 G to the power Z0 modulo N, compute Z1, which is the following, and then again Y2. Then if Y1 is Y2, you accept, else you reject the signature. Okay, so steps 4, 5, 6, 7, 8, 9 is known as the KAZ-SIGN digital signature forgery detection type 1. 10 until 15 is called procedure type 2. 16 until 22 is type 3. 23 until 29 is type 4. Okay, so the design rationale as the proof of correctness, steps 30 until 37, it is a simple algebraic manipulation using simple mathematics that anybody can understand directly. Okay, so you get G to the power Z0 is equals to G to the power Z1 because alpha is V1 modulo GRG. As you can see here, this alpha here is on the second tier. So the first tier is R, the second tier is alpha. So when you do modulo N, the order will kick in and you will have alpha modulo to the order of R inside the modulo of the order of G in N. So that's why you get this result. Okay, as for type 1, if you have a valid signature, you will not get W1 equals to 0. So it means that a valid signature will not be rejected. As for type 2, you will get W3 is not equal to 0. Hence, a valid signature will not be rejected. The following procedure, type 3, you will get a valid signature to be equal to 0. Hence, it will not be rejected. As for type 4, you have W9 equals to 0. Hence, a valid signature will not be rejected. Okay, so what are the types, what are the structures of signatures that fall under the category that will be rejected? So you have these two signatures. The first signature utilizes directly the public key inside the signature. And the second one is utilizing alpha F, which is V1 modulo GRG, which is publicly available. And these two equations will pass the final step, steps 30 until 37. However, it will be rejected by type 1 and type 2 detection procedures. For type 3, these are the equations. This one was highlighted by Bernstein, especially adding the order inside the signature and utilizing the public variables available to the adversary. And all these four will pass type 1 and type 2. It will also pass the final procedure, but it will not pass the type 3. The reason is because as given point 1 and point 2. Okay, an alternative for the adversary, as you can see, the adversary would like to have this relation to hold. So the adversary would want to have his own parameter S1 such that the equation will hold. So this is the equation that the adversary would want to happen. However, to solve equation 1, the complexity is OQ. So when deploying Grover's algorithm, it's Q to the power 0.5. And since Q is a prime, then where it's 128 or 19256, the adversary will not be able to execute Chinese remainder theorem to reduce the complexity. What about type 4? Type 4 is when an adversary changes the modulus. The prescribed modulus is using Q square. So the adversary uses another prime, rho, which is unknown to the verifier, and uses it to do the modular. So it's modular GRG rho Q instead of Q square. So this type of forgery will pass type detection 1, detection 2, and detection 3. It will also pass 30 until 37. However, it will not pass detection type 4. Basically because it's in different groups. And here we are using the public parameter V1. So what if we replace V1 with alpha F like in the previous procedures where we have the pair? The first signature, the forge, we use V1 and then we use alpha F. So in this case, if you use alpha F in the equation, it will not pass type 3, so you don't have to go until type 4. Okay. What about if you try to extract alpha modulo GRGQ square from S2? The algebra suggests that the complexity is OGRG2Q square, where GRG2 is GRG divided by GS1R. Okay. What about if we try to extract alpha from the digital signature forgery type 4, the procedure type 4? In fact, through the detection procedure type 4, one can actually extract the value alpha modulo Q square. So this is possible. This is possible. And then the challenge faced by the adversary is to retrieve alpha from alpha mod Q square. And this is the modular reduction problem. And since GRGQ is less than Q square, the complexity of the MRP via V1 is much higher than the complexity of solving alpha mod Q square. As such, the complexity of solving MRP via alpha mod Q square will be the determining factor in identifying the suitable key length for each security level, meaning that the reduction value modular Q square is less than the reduction value under GRGQ. Hence, you need the adversary will target the lesser value, which is modular Q square. So we need to increase certain parameters such that to solve MRP on alpha mod Q square will be exponential according to the security levels that we wish. What about if we target the linear equation S2? So the linear equation S2, after some manipulation, we end up with the final equation, which is RF alpha S1 minus VS1 plus HR plus HRF 0 mod GRG2. Here, RF is a public value. Alpha to the power S1 is unknown. VS1 is known. H is known. R is unknown. H is known. RF is known. So here we utilize Herman-May's conjecture. So let alpha hat be the upper bound for alpha S1 and R hat be the upper bound for R. If alpha hat multiply R hat is much larger than GRG2, there's no efficient algorithm to output all the roots. So to this end, alpha S1 is exponentially large. It is clear to conclude that this occurs. This implies there's no efficient algorithm to output all the roots of 4. Now, in our first submission, we decided to use this as the underlying reasoning of the discussion. which is the second order discrete logarithm problem. It's about trying to solve a discrete log problem and a second order discrete log problem as given by 5. You have given G, you are given Q, you are given A, you're given N, what is X? Okay, so in order to solve this, the first level of discrete log problem is easy. It's supposed to be easy. Then you will receive the exponent. Then you need to solve for the second exponent, which is X. The complexity of such procedures is the same as solving the modular reduction upon X on the order of Q in the order of G in N. So basically, if you try to use this as the underlying hard problem for the design, it's expensive. So you don't need to actually discuss this in detail because it falls down back to just this relation X naught congruent X modulo GQG. Okay, as such, we have the following table. If the modulus N contains 195 primes, we have the security level of 1 to 8, which means alpha modulo Q square, the reduction value is exponential 2 to the power 1 to 8. Then the public key size is 474, the private key size is 384, signature size is 700, and this is the comparative with elliptic curves. If you use the number of primes in the modulus N, 290 primes, the modular reduction on alpha modulo Q square is 192, and as follows, the key size is 588 bits, and so on and so forth. And for level 5, it's as follows. I forgot to put in the timing, so it's on the website anyway. For the first level, for 1 to 8, the key generation for 100 keys is 108 milliseconds. For signing is 384 milliseconds, and verification 161 milliseconds for 100 sets, and so on. Okay, which comes to the current comment by Bernstein on the document uploaded on our website on V1.3. With high probability, a public key and sign message for KAZ-SIGN version 1.3 would allow the following script to forge signatures on attacker chosen messages under that public key. The script checks that the signatures pass verification with the reference software. The success probability is 93 over 100, 90 over 100, 90 over 100 for 1662, 267, 3783 directories respectively. Now, this comment should couple with his previous comments, meaning that the previous comments were not discussing such attacks initially. The attacks that were discussed initially were about forging using known public parameters, which gives you a 100% forgery mechanism. Now, in 1.3, after addressing his comments, it has been reduced to 90%. So what does it mean, basically? It means that the team needs to study the 10% that could not be utilized. So we zoom in into the 10% which could not be utilized to forge signatures under the chosen message for corresponding public key set. Then, to utilize these algebraic structures upon all signatures to be generated with minimum amendment. So we do not actually need to amend 1.3 anymore. We just need to put in the filtering according to the current structures that we can identify from the 10% that is not able to forge the signatures. So we aspire to only include additional filtering procedures during signing and verification, and no changes upon key gen, and no additional parameters to be introduced. So no new keys and signature parameters, and not to increase the key size and signature sizes, and we will make it public as a 1.4 later on. Now, so back to the original question, is it possible to get the secret key from the public key? It is the modular reduction problem. Up until, the publication was on 31st May. Up until today, it's still not answered. But basically, it's a big number, chop off, becomes small. So what was the original large number, right? So then you have the reduction. then you need to know what is the correct reduction value in order to get the big number again. Then it is utilized using a 3-tier exponential modulo n. Hence, you can actually pass the final verification because you have the public parameter which is modular the order of the second level discrete log. So with doing that, we are able to identify if the signature was doing that. Hence, you can omit, omit, and omit each time you receive a signature. Okay, so I think that's about it for this afternoon. So I would like to thank Professor Nitaj from France, Bernstein, NST team, and for MI Oxford and PQC for organizing this event. With that, thank you and terima kasih.